Demonstration problem. If the coefficient of static friction between a 50-pound crate and the floor is mu sub s is 0.4 and the coefficient of kinetic friction is mu sub k is 0.30. Part A. Once the crate is in motion, what horizontal force or push must Cuthbert provide to move the crate at a constant velocity of 7 meters per second? In other words, what is this push that Cuthbert must provide? We construct the force diagram by drawing the crate and all bodies that touch the crate, in this case the floor and the push. We look at the forces, contact forces and field forces. The field force is the weight, or the gravitational force. F sub W is the weight, or mass times the acceleration of gravity. The other y-axis force is the normal force provided by the floor on the crate. Cuthbert pushes the crate, we call that Fc, and the kinetic friction force in this case acts in response to that. It's kinetic friction or sliding friction because the body is in motion. Then we collapse the crate to a particle at its center of gravity. We put the tails of all the vectors at the origin, and we see that the push vector provided by Cuthbert is opposed by the frictional force vector provided by the surface between the bottom of the crate and the floor. The normal force balances the weight. For part A, the givens are mu sub s, the coefficient of static friction, is 0.4. Mu sub k, the coefficient of kinetic friction, is 0.3. No units for either one of those. V sub x, or the velocity along the x-axis, is constant at 7 meters per second. Since acceleration is a change in the velocity over the time, and the final velocity is 7 meters per second, and the initial velocity is 7 meters per second, the acceleration along the x-axis is 0. The weight force is 50 pounds in magnitude. It acts downwards. Since the surface is horizontal, even though the crate is in motion horizontally, it is moving neither upwards nor downward. Therefore, the velocity along the y-axis is 0, which is a constant. It's at rest along the y-axis. And the acceleration along the y-axis is also 0. For part A, the unknown is, once the crate's in motion, what horizontal force must Cuthbert provide to move the crate at a constant velocity of 7 meters per second? We need to know F sub p is what? What is the equation for part A? We see that the crate has constant velocity along the x-axis, it's in uniform motion, at 7 meters per second, and the velocity along the y-axis is also constant. It's a constant 0. It's at rest along the y-axis. Therefore, Newton's first law applies along both the x and the y-axis. Our equation is the net force, or the total force, along the x-axis is 0, and the total force, or net force, along the y-axis is also 0. Substitute. First along the x-axis. Applying Newton's first law, total force is 0 along the x-axis. So we write F net of x is, and to get the total force, we must go to our force diagram. We see that we have pushing force by Cuthbert, which is positive. We write F sub p. And we see that the frictional force is negative, so we write plus or minus the frictional force. That's 0. Solve for F sub p, the pushing force. And in magnitude, the pushing force is the force of friction. Since the block is in motion, this is not static friction, it is kinetic friction. And that formula is the frictional force is the coefficient of kinetic friction, mu sub k, times the normal force. We have that the push is the frictional force in magnitude, or the coefficient of friction, mu sub k, times the normal force. Substituting along the y-axis, we also have that the total force along the y-axis, or F net of y, is 0 by Newton's first law. We once again go to the force diagram to get the forces along the y-axis. We see that the normal force acts upwards to balance the weight force. So we write normal force, which is positive, minus the weight force is 0. We solve for the normal force. We get that is the weight, and the weight is a given of 50 pounds. We're now ready to solve part A. We had previously that the pushing force by Cuthbert has in magnitude the frictional force, which is mu sub k times the normal force. So we write F sub p is mu sub k times the normal force. We substitute in for mu sub k a value of 0.3 with no units, and the normal force we substitute in 50 pounds. We get that Cuthbert must push at a force of 15 pounds to continue the motion of the crate along the horizontal surface at a constant 7 meters per second. Note that it doesn't matter that the value of the x velocity is 7 meters per second. It only matters that it's constant. It could be 17 meters per second or any other value. If we applied a pushing force, or if Cuthbert did, of greater than 15 pounds, then the crate would accelerate. If he applied less than 15 pounds, then the crate would slow down.